All right, in this video, we're going to look at how does the combination of uh, scalar multiples of one row being added to another affect the determinant of a matrix. This is a common elementary row operation that we use to solve systems, and so we're going to see how doing that here can affect the system. So uh, in the notes, you'll see that the matrix A has a certain form, which you see here. So it's a 3 by 3 matrix, a square matrix, where the first row has A, B, and C. The second row has A plus B, and A plus C in the third entry of the second row. And then 2A plus B, and 3A plus 2B plus C. Okay, so we're going to take a look at this matrix. I first wanted to compute the determinant here, and as you see, uh, inputting that, the determinant came out as A cubed. So the next thing I want to show in this video is looking at elementary row operations for this matrix, and then computing the determinant of it to see if, in fact, we get the same result. Okay, so with that, we're going to go ahead and move over to my handy dandy little second camera here and get to work on reducing this matrix via row operations. Okay, so the first thing is I'm going to turn this into an upper triangular matrix. So I want to remove these elements from each of these. So just like before, I'm going to take a -1 times row 1 and then add it to row 2, which is a fancy way of saying subtracting row 1 from row 2. Okay, and doing that, A, B, and C remain the same. So take away A, this becomes 0. Take away B, this becomes A, and then take away C, this becomes A plus B. And then doing the same thing, negative row 1 and adding it to row 3. So negative A to A gives me 0. Negative B plus this gives me 2A. Negative C plus this gives me 3A plus 2B. Okay, so I have reduced these two elements to both zeros, and so now I want to remove this bottom element here from this to make this 0, and then it'll be upper triangular, and then we can use that property we saw earlier this week when we have a special form of either upper or lower or diagonal to compute the determinant. So the nice thing is here I can multiply 2 times row 2 and add that to row 3. And if I did that, then A, B, and C. So the top part stays the same. Negative 2 times here because this is 0. And actually, I can say that the second row doesn't change. Okay, and so going here, I go negative 2 times that is negative 2A, and adding that to 2A gives me 0 there. Going negative 2 times here, you're going to get negative 2A minus 2B. And so you get only 1A remaining, and the B's cancel out as well. And so we now have this in upper triangular form, which is really, really helpful because we saw that when we were calculating the determinant, all we have to do is multiply the diagonal elements, which you can see right away is A times A times A, which is A cubed, which is what we would expect. But just to be sure, let's go ahead and we'll go ahead and expand a cofactor expansion along this first row. Notice that we have these two elements of zeros here, which makes this calculation exceptionally nice. I should also include my equal signs here. So A is the first element. And if I look just at this submatrix right there, I have A plus B times 0, and A minus, and because the second element is 0, I don't have to worry about what this matrix looks like because it's going to be multiplied by 0, and then plus 0 for this third element in the column, the first column of A. And again, I don't really care what those elements are because they're getting multiplied by 0. So all of this term is 0, and the only thing I'm left with is the small determinant here. So I have A times A, and I think you can probably see it already, but that's A squared, A times A. And then the second term is being multiplied by 0, so it's canceling out as well, which is indeed exactly what we expected. So we get A cubed, which is what we got from the doing the full determinant in GeoGebra. So again, this demonstrates that in general, when you multiply one row by another and add them together, it does not affect the determinant of the resulting matrix. I hope that was helpful, and I look forward to seeing you in the next